Good day and welcome back to part 2 of our discussion of double integrals over general regions. In the previous video we introduced kind of the need to be able to evaluate integrals over non-rectangular, i.e. general regions. And in this video what we'd like to do is cover a worksheet, pages 2 and 3 of our note handouts, that I had requested that you all spend some time thinking about. And as mentioned, if you missed the end of the last video, this is something I would pass out in class, give students roughly 25-30 minutes to work through in groups as I interacted with them. So hopefully you've taken the time to look through this, think about the material ahead of time, and what we'll do in this video is talk about how we can set up our limits of integration, that is, turn this double integral into an iterated integral that we can evaluate using our techniques of integration. And our approach for setting up these limits of integration is going to be almost solely based upon the region D. And in this section we specifically will look at two types of regions. Regions that our book are going to call type 1 and type 2. And we're starting off with the type 1 regions. And I will occasionally refer to things as a type 1 or type 2 region, but you don't need to do so. It's really kind of the thought process and the intuition that we are going to develop. So stated as intuitively as possible, a type 1 region is a region which is bounded by two, continuous functions of x. Here a smaller function y equals g1x in blue, and a larger function y equals g2x in red. So really we think of this as a region that's kind of almost bounded vertically by functions of x. So if you haven't done so already, pause the video and draw two more examples of these type 1 regions. I will also draw several generic regions in as well, and I'm going to start off by picking something that should be familiar in the sense that we saw it in our previous video. So how about we pick this larger function to be a line segment, and our lower function to be a horizontal line segment making up the y-axis. So that our region D, let's call it in this case, is this triangular region bounded by, in this vertical sense, by these two continuous functions of x. Something else that we will frequently encounter will be things that are circular. So another thing we could think is a circle of, let's call it any radius we want, but let's say 1, centered at the origin. We could think of the top curve bounding our region as the upper half of the circle, and the bottom half making up the lower curve. So that our region is this disk centered at the origin, and this would be an example of a type 1 region. And now is where we get into the setup. So for a double integral over one of these type 1 regions, so something that we can think of as being bounded vertically by two continuous functions of x, is as follows. And this is my intuition. When I look at this region that we have above, so it's bounded above and below by these functions of x. Those are going to be the inside limits of integration. This is something that works very nicely in the y direction. And then our limits of integration are going to be on the outside. So we think our x values for our region vary between a and b. That gives us our outer limits of integration. Then what we need to think about is if we choose a value of x, it doesn't matter which one between a and b, how do those corresponding y values vary? And they're going to vary along these vertical lines going from the lower limit of g1 to that upper limit of g2. And this is how I kind of visualize sitting in these limits of integration. And I realize this is all very abstract, so let's go to this nice concrete example. Let's sit up, and we're not going to worry about the valuation, the limits of integration for the double integral, where D is the region bounded by the parabola y equals 2x squared and y equals 1 plus x squared. And I guess you should double check with me before proceeding. Let's sketch these. So the shapes of these graphs are going to be very similar to each other. So now y equals 2x squared is a parabola opening upward with a vertex at the origin. And the fact that it's a 2x squared opposed to, say, just a single x squared, would indicate that it's just a bit skinnier, or grows a bit more quickly. Then the graph of 1 plus x squared is the standard parabola y equals x squared, but it's shifted 1 unit upward in that positive direction. So it's going to be wider than 2x squared. So in black we have y equals 1 plus x squared. In blue we have y equals 2x squared. And we can hopefully now very clearly see this region D enclosed between them. So the first step towards setting up the limits of integration is to sketch this region D of interest. Now we would like to take our thought process from above and turn this into an iterated integral. That is, we need to determine our order and our limits of integration. And my thought process looking at this is I'm seeing something that is varying very nice between continuous functions of x's. So that's telling me that I can put dy on the inside, because we're varying between functions of y, and then we're going to have to throw dx on the outside. And I start off with my outside limits of integration, which should be numbers, and in this case those numbers would correspond to the x values where these curves intersect each other. So a part of this problem is going to be finding the intersection of the two curves. That is, for what x values is 2x squared equal to 1 plus x squared, i.e. x squared is 1, or x is equal to plus or minus 1. So our outer limits of integration are going to be how the x values in our region vary. We're varying from a lower limit of integration minus 1 to an upper limit of integration 1. So our limits of integration on the outside will be minus 1 to 1. Then we need to think about, if we pick an x value between minus 1 and 1, just a generic representation, how do the corresponding y values vary? They vary from this lower curve, 2x squared, until we hit that larger curve, 1 plus x squared. And that's exactly our limits of integration. The lower limit, 2x squared, the upper limit, 1 plus x squared. And this really completes what I consider to be the new part of this process. We've set up an iterated integral that we could now evaluate. But once again, let me remind you of the thought process. We see this region bounded between two continuous functions in that vertical y direction. So I'm going to make y the inside limit of integration, which forces x to be on the outside. So for our region, we think, how do the x values vary? Those numbers, remember the outside limits of integration are always numbers. What are those corresponding inside limits of integration? Now that we've spent some time introducing the concept of a type 1 region, let's just note not every region will be type 1. There are also regions that might be what we call type 2. That is, instead of a region that varies, previously in that vertical direction between two functions of x, it's very reasonable to have something such as the picture here, where it varies horizontally between two functions of y. So note how we would describe this. We would say that x values lie between h1 and h2 of y, and then the y values lie between constants c and d. So let's see if we can go ahead and fill in these limits of integration to turn this double integral over the region D, pictured above, into an iterated integral that we could hypothetically evaluate. And remember, the key here is that we need to have numbers as our outside limits of integration. So if we think about it from that perspective, this is varying nicely in that y direction from c to d, which would give our outside limits of integration. So c and d. And now for a value y, think any generic one, between c and d, how do those corresponding x values vary? And those x values vary along these red horizontal lines going from the lower function h1 to the upper function h2. So our inside limits of integration will be h1 of y up to h2 of y. And whenever I'm setting up my limits of integration, I will almost always, at least whenever is possible, sketch the region out, and based upon whether it's type 1 or type 2, I'm going to be drawing these little horizontal or vertical lines to think about what my inside limits of integration will be. It is a very useful technique when you're going about setting up these limits of integration. Let's look at a nice concrete example. We will go ahead and evaluate the double integral over some region D of 2x plus y squared, where D is the region bounded by x equals y squared and x equals y cubed. Now, the first difficulty for a problem of this form is most likely sketching this region of integration. We are almost always working with functions of x, so it requires a bit more thought when we're dealing with functions of y. Let's see if we can talk our way through this. If I would like to sketch x equals y squared, that should be a parabola opening up along the positive x-axis with a vertex at the origin. Just think kind of mentally, what does y equals x squared look like? So in blue, we have the curve x equals y squared. We would like to now add to this the function x equals y cubed. So I want to think, what does that standard cubic look like? But we need to do so in a sense that we've switched around the roles of the x's and the y's. So in terms of x equals y cubed, remember, when y is positive, x is positive. When y is negative, x is negative, and it's a cubic. Roughly speaking, what this would look like is the following. So they're negative together, cubic, and then the cubic's going to grow faster than the quadratic. So in black, we would have the graph of x equals y cubed. And if we really focus in, I'm going to zoom in just a little bit, we can see this sliver of a region enclosed between those two graphs. And that will correspond to our region of integration, D. And once again, let me just note that sketching this region is certainly not an easy thing for us to do, but with practice it does become easier. Another technique that you could use to go about this would be to sketch the functions where you've switched around the variables. That is to say, you could instead sketch y equals x squared and y equals x cubed. But remember, this isn't what we want. We want the x's and the y's to be opposite of each other. So what we could do is, after we sketch and determine our region, is we could then reflect about the line y equals x. So this gives maybe a slightly alternative approach. My preferred method is to kind of just think our way through it, and for the types of functions we will encounter, typically things that are lines and quadratics, this will be a very reasonable approach. And for this problem at hand, in order to set up our double integral, i.e. turn it into an iterated integral, we need to find the points of intersection between these two curves. That is, we need to solve, in this case it will be for the y values, where y squared is equal to y cubed. So note, this is equivalent to saying 0 is y cubed minus y squared. Or you could factor out a y squared, and this would imply for us that y is 0 or y is equal to 1. So y equals 1 would correspond to that upper point of intersection. And note, we do not need to know the actual point, which is 1, 1. It's just the y coordinate that's going to be useful. The double integral over D, we're viewing this as one of those type 2 regions. So we are going to set it up with y as our outside variable of integration. And note on the outside, our y values are varying nicely between 0 and 1. So those are the numbers that we need as our outside limits. And then we just simply ask for a generic y value between 0 and 1. How do those corresponding x values vary? And they vary from this lower black curve to the upper blue curve. And note when we are thinking of functions of y, they are of this form x equals. So a smaller thing is smaller in terms of x, so to the left. A bigger thing is bigger in terms of x, so the larger quantity is to the right. So our inside limits of integration are varying from that lower curve, y cubed, to the upper curve, y squared. And note we're measuring lower and upper in this x direction. And now that we have our iterated integral set up, and I do look at this as the new and most difficult part of the problem, let's go ahead and evaluate just to get some practice. So as a first step, we will anti-differentiate inside with respect to x. So x squared plus y squared x, remember we treat that y squared as a constant, and we're evaluating from x equals y cubed to x equals y squared. So we replace each x with a y squared, so that's going to be y to the fourth plus y to the fourth. Minus sign, we replace each x with a y cubed. Y cubed squared is y to the sixth plus y to the fifth. And combining terms, we have the definite integral from 0 to 1 of 2y to the fourth minus y to the sixth minus y to the fifth. Then anti-differentiating, we would have 2/5 y to the fifth minus 1/7 y to the seventh minus 1/6 y to the sixth, all from 0 to 1. So substitute in a 1 to get 2/5 minus 1/7 minus 1/6. Subtract away what you get when you substitute in 0, which is 0. And this number that we end up with is a perfectly acceptable form for the solution. You do not need to do any more algebra or arithmetic to combine this together. And at this point, I always think it's worth just making the quick observation of what should your work look like when you submit problems for homework or on exams. And it would be hard to complain if your work resembles kind of what we've shown here. We should have a sketch of what our region of integration looks like. If we need to find any points of intersection, we should have that associated algebra. And then our integral should be evaluated using good notation. So we convert it to an iterated integral. Step by step, we incrementally work our way through. We show all equal signs, all limits of integration, all differentials. And it should be nicely organized and hopefully easier for me to follow. A general rule of thumb is that you want who's ever grading and trying to provide you feedback to be as happy as possible with your work. So that completes the material for this video, which is introducing these type 1 and type 2 regions. What we will talk about in the next video is how some regions, maybe even the one included here, are both type 1 and type 2 regions, and how and why we might want to interchange between one or the other. So stay tuned and take care.